Welcome to Maths with EJD. In this video, I'm talking about bifurcation theory, and so we need to understand what bifurcation is all about, right? So, for starters, bifurcation theory studies how the qualitative nature, how the qualitative nature of solutions qualitative nature of solutions to dynamical systems changes when a system parameter is varied. When a system parameter is varied. So as you vary a parameter, what happens to the system? That's what bifurcation theory studies. And then when we talk about a bifurcation in particular, a bifurcation occurs when a small change, when a small change in a parameter causes a sudden qualitative change. Maybe a system that was stable before automatically becomes unstable because of a little change. So causes a sudden qualitative change in the system's behavior. In the system's behavior. Okay. So this can this can lead to the appearance or disappearance of fixed points when you perturb the system. It can lead to appearance or disappearance of the system of the fixed points, or it can actually lead to changes in stability. Maybe something that was stable becomes unstable, or something that was unstable becomes stable, and all that. Or the onset of oscillations. So something that was not oscillating can begin to oscillate, or it can lead to chaos where the system, is out of sync, right? So having talked about this, we can then go up and talk about bifurcation diagrams, right? So we have bifurcation diagrams. Okay. So a bifurcation diagram is a graphical representation. It's a graphical representation that shows how the equilibrium points, how the equilibrium points of a dynamical system, okay, such as fixed points or periodic solutions evolve as the control parameter changes, as the control parameter changes. Okay, these diagrams illustrate transitions. They illustrate transitions from stability to periodic or chaotic behavior. Okay. Now so an example of this will be that it will be the kind of thing we have in a logistic map. So in the logistic map, in the logistic map, xn plus 1 equals rxn into 1 minus xn, for instance, as the parameter r, as the parameter r increases, as we keep increasing parameter r, okay, the system undergoes a series of bifurcations, as we're going to see very soon. The system undergoes a series of bifurcations showing the transition, from steady states to periodic cycles, and then chaotic behavior. Okay, so now we switch over to talk about types of bifurcation. So types of bifurcation. So first of all, we have what we call the saddle node bifurcation. Saddle node bifurcation. I mean, I think 2 videos before now we talked about uh, how to classify equilibrium points, and the first one we saw was node, unstable node and stable node, where you have real values for eigenvalues and they are both of the same value. So when they are both positive, that's unstable node. When they are both negative, that's stable node. But when we go to saddle, you know, the values, one is negative, one is positive, then you have saddle. So you have saddle node bifurcation. So from a saddle, you now have a node. So that's from that. So this actually occurs, saddle node bifurcation occurs, okay, when two fixed points, that is one stable, you know, that's a saddle for sure. One stable and one unstable, okay, they collide and annihilate each other, each other as a parameter is varied, So a good example of this, very good example of this is when you have dx dt equals r, dx dt equals r minus x squared, okay, where for r equals 0, you know, for r equals 0, the two fixed points, merge and vanish. So the two fixed points merge and vanish, okay? So from saddle, you have a node, okay? So that's about saddle node bifurcation. So we have number 2, that is what is called a transcritical bifurcation. Transcritical bifurcation. Okay, so here you have two fixed points. In transcritical bifurcation, two fixed points exchange stability as a parameter changes. The exchange stability as the parameter changes. Okay, so an example of that would be in the equation, dx dt equals rx minus x squared. Okay, so the stable and unstable points, cross. The stable and unstable points cross as r decreases. So we're going to see these pictures on using Python pretty soon. And then we have, that's number 2, right? Transcritical bifurcation. Then we have what is called the pitchfork bifurcation. Pitchfork bifurcation. Okay. So for in a pitchfork bifurcation, okay, a system with a symmetric equilibrium, a system with a symmetric equilibrium undergoes bifurcation, where a stable equilibrium, a stable equilibrium point, a stable equilibrium point splits, okay, or merges with others, resulting in a bifurcation diagram shaped like a pitchfork, shaped like a pitchfork. So there are 2 types of this. There are 2 types. Okay. First, we have the supercritical, pitchfork bifurcation. Okay. So here you have that a stable equilibrium splits into 2 stable equilibria. Okay. As a parameter is increased, and the original equilibrium becomes unstable. Okay, so a very good example of this is when you have dx dt equals rx minus x cubed. Okay, so with this now, for r bigger than 0, the system has one stable equilibrium at x equals 0, but as r increases, the equilibrium becomes unstable, okay, and 2 new stable equilibria form symmetrically, at x equals plus or minus square root of r. Okay, so that's supercritical pitchfork bifurcation. On the other hand, we have what you call the subcritical. You have the subcritical pitchfork bifurcation. Okay, so for the subcritical, for the pitchfork bifurcation, two unstable fixed points merge into a stable equilibrium, into a stable equilibrium, okay, as a parameter changes, as a parameter changes. An example of this would be when you have dx dt equals r minus x squared, where for r less than 0, the system has two unstable fixed points, two unstable fixed points, okay, which merge into one stable fixed point as r increases. Okay. So lastly, we have what you call the what you can call the Hopf bifurcation. So that's number 4 now. Number 4, we have the Hopf bifurcation. So in a Hopf bifurcation, a stable equilibrium becomes unstable and gives rise to periodic behavior. A stable bifurcation becomes unstable and gives rise to a periodic behavior. I mean, talking about limit cycles, like when we talked about center the other time, something like that. So just orbiting the critical point. So an example of this is the Van der Pol oscillator. The Van der Pol oscillator. The Van der Pol oscillator exhibits periodic behavior when the control parameter, crosses a critical value, marking a Hopf bifurcation, Okay, so to see these things clearly, let's see the let's see what Python code has. So for saddle node bifurcation, right, we talked about r minus x squared. Of course, if you equate that to 0, right, you're going to have say, x squared will be equal to r. That's plus or minus r. And then as that changes, right, when r is greater than 0, you have real numbers plus or minus of that. So, and that means that's going to be unstable. But then as the value goes below 0, then you begin to have negative. You're going to be having strictly, I think that will be strictly complex numbers, and that is going to lead to limit cycles or something like that. So, so for saddle node bifurcation, this is what you have. You have r minus x squared. So, and so if I run that, see what you have. Mm, so you have some kind of transition going on there as the value of, so the x dt on that side and x on this case. So you have saddle node bifurcation. Okay. Then for the next one, you have transcritical bifurcation, where I think two stable also. Oh, okay, let me even see. So for saddle node, right? The condition for saddle node is that you know, it occurs when two fixed points, one stable and one unstable, collide and annihilate each other as the parameter is varied. So for r equals 0, right? The two fixed points merge and vanish, basically. So And then for transcritical bifurcation, you have two fixed points exchanging stability as the parameter changes. For instance, if you evaluate the x dt equals rx minus x squared, if you equate that to zero, right, you're going to have like x into r minus x equals zero. So x is zero and r is equal to x. So as so in the equation, right, the stable and unstable points cross as r decreases. So as r decreases, the stable and unstable points cross. So you see the crossing happening, at x equals zero, you can see stable and unstable crossing. I think the unstable is coming from above and the stable is coming from below. So the anything greater than zero will be unstable, right? So you see that dark green, something is that purple now? That's the unstable side, and the yellow one in the beginning is the stable side. So by the time it's x gets to zero, then you have a crossing over. The stable becomes unstable, and the unstable becomes stable or something like that. So they merge at two fixed points, exchange stability as the parameter changes. So unstable becomes stable, unstable becomes unstable. So for pitchfork bifurcation, a system with a symmetric equilibrium undergoes bifurcation, where a stable equilibrium point splits or merges with others, resulting in a bifurcation diagram shaped like a pitchfork. So if you run this, we see that pitchfork kind of shape. So see what that looks like now. So um so in this case now, for values coming from above, you have that purple side, and then it's unstable, and then for the yellow side now, you have that switching over taking place when x is equal to zero right there. Okay, so I think we're going to see hop bifurcation in the next video because there talking about um I'll be talking about um, still, I'll be talking about bifurcation, but then as it leads to chaos. All right. Because in this chaos and cycles and everything. So let's see how that goes. So watch out for the next video where I'll be talking about bifurcation and chaos. So this is an introduction to bifurcation theory. Uh, and you have an idea already that, stability changing or things, I mean, different things taking different shapes as a parameter is varied over time. So thank you so much for listening to this. Let me know in the comment section how helpful these videos are for you. And if you'd like me to teach a topic or solve a problem, feel free. I may be able to find time along the line to do that. And if you have subscribed to this channel, thank you for that. If you have not, please go ahead and do that right away because there's a lot still coming. For instance, after I'm done with this, but in the next video, I'll be talking about bifurcation and chaos, chaos, of course, talks about some kind of disorderliness in dynamical systems. So we'll be talking about that. So after this, I'll be moving on to Laplace transforms. That'll be a whole playlist on its own, but then I'm going to merge it with differential equations because Laplace transforms helps us to solve problems involving differential equations, right? So be sure to hit the notification bell so you can always get alerted anytime a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.